When I first saw the transmission logs from China's Tianwen-1 orbiter, I didn't move for several seconds. Not because the data itself was shocking, though it certainly was, but because of what it meant. For the first time since we discovered 3I/Atlas back in July 2025, we had a spacecraft observing it from a completely different vantage point. Not a ground telescope fighting through Earth's atmospheric distortion, not even Hubble or JWST, magnificent as they are, but a probe actively orbiting Mars, positioned at roughly 30 million kilometers from the most perplexing object currently traveling through our solar system. And what Tianwen-1 captured during those 30 seconds of continuous imaging changed the entire conversation we've been having about this visitor. You see, when you observe an interstellar object from Earth, you're always looking through a filter, literally. The atmosphere scatters light, blurs edges, introduces noise. Even adaptive optics can only compensate so much, but Tianwen-1's high-resolution camera operates in the vacuum of space with zero atmospheric interference. The clarity it achieved is extraordinary, and what it revealed has forced us to reconsider several assumptions about how matter from beyond our solar system behaves when it encounters our star. Let me take you back briefly to put this in context. 3I/Atlas was discovered on July 1, 2025, by the Atlas Survey Telescope in Rio Hurtado, Chile. Within days, astronomers confirmed what made their hands shake slightly as they typed up the initial reports. This object's trajectory didn't originate from the scattered disk beyond Neptune. It didn't come from the Oort cloud. The orbital mechanics were unmistakable. This thing came from interstellar space, making it only the third confirmed visitor from beyond our solar system after Oumuamua in 2017 and Borisov in 2019. But unlike its predecessors, 3I/Atlas immediately began displaying behavior that defied our models. Oumuamua famously showed no cometary activity whatsoever, remaining stubbornly inert and tumbling through space like a cosmic cigar or pancake, depending on which interpretation you prefer. Borisov behaved like a textbook comet, releasing carbon monoxide and dust exactly as our theories predicted. 3I/Atlas? It's been rewriting the rules since day one. The first anomaly appeared in late July 2025, when the Swift Observatory detected something that shouldn't have been possible. At a distance of nearly 3 astronomical units from the Sun, well beyond the frost line where water ice typically sublimates, Swift's ultraviolet sensors picked up the characteristic glow of hydroxyl radicals, OH molecules, the smoking gun signature of water vapor. Now you might think, okay, a comet releasing water vapor, what's the big deal? Here's the problem. At that distance, the solar radiation simply isn't intense enough to heat a comet's surface to the point where water ice directly sublimates. The physics don't support it. When Zexi Shang and Dennis Bodewitz published their findings after stacking over 2 hours of ultraviolet exposures, they weren't just reporting a detection. They were documenting something that challenged our fundamental understanding of cometary outgassing mechanics. Their interpretation? The water vapor wasn't coming from the nucleus surface at all. Instead, near-infrared observations from Gemini South and NASA's Infrared Telescope facility revealed something remarkable. Large chunks of ice, icy grains, were floating in the coma surrounding 3I/Atlas. These fragments, ejected from the nucleus by the outgassing of more volatile substances like carbon dioxide and carbon monoxide, were acting as distributed sublimation sources, miniature steam vents scattered across thousands of kilometers, each releasing water vapor as sunlight warmed them directly. Think about that mechanism for a moment. It's like the comet created its own secondary outgassing network, a distributed system of ice chunks turning into vapor far from the nucleus. Bodewitz described it as water leaking like a fire hose, which is vivid but perhaps understates the strangeness. This isn't a garden hose with a steady stream. This is a fragmented, chaotic system where the traditional distinction between nucleus and coma becomes blurred. As summer progressed and 3I/Atlas continued its inbound trajectory toward perihelion, the astronomical community mobilized. The Vera C. Rubin Observatory, newly commissioned and conducting science validation observations, serendipitously captured the comet between June 21st and July 3rd. Those images showed something subtle but significant. The coma diameter was increasing. The nebulous envelope around the nucleus was expanding as the comet warmed. Then came JWST's first observations on August 6, 2025.
NASA announced the results on August 25th, and the data from the near-spec instrument added another layer of complexity. The spectroscopic analysis revealed compositional details that didn't quite match standard solar system comets. The ratios were off. The chemical fingerprint suggested formation conditions different from what we see in objects born in our own planetary nebula.
By early September, the James Clerk Maxwell telescope joined the observation campaign. At 2.33 astronomical units from the Sun, they detected hydrogen cyanide at a production rate of about 1.5 times 10 to the 25th molecules per second. 1 week later, that rate had tripled to 4.5 times 10 to the 25th molecules per second, 2 kilograms of hydrogen cyanide every second. The outgassing was accelerating dramatically as 3I/Atlas approached the Sun. But here's where the Tianwen-1 observations become absolutely critical. See, all those previous measurements, spectacular as they were, came from Earth-based facilities or space telescopes in Earth's vicinity. Same general perspective, same angle, same light-scattering geometry. What we desperately needed was a completely different viewpoint, and that's exactly what China's Mars orbiter provided when it turned its high-resolution camera toward 3I/Atlas in late October 2025. The images, transmitted back to the Beijing Aerospace Control Center and released to the international community on November 5, revealed structural details that simply weren't visible from Earth's perspective. At 30 million kilometers distance, Tianwen-1's camera resolved features within the coma that appeared at first glance to show asymmetry. Not the gentle, predictable asymmetry you'd expect from solar radiation pressure pushing dust and gas away from the Sun. No, this was different. Localized brightening in regions that didn't correlate with the expected sublimation zones. The Chinese team, led by researchers at the National Space Science Center in Beijing, immediately shared the raw data with NASA, ESA, and JAXA through established protocols. Within hours, analysis teams worldwide were applying photometric reduction algorithms, comparing the Tianwen-1 images against simultaneous observations from ground telescopes. The confirmation came quickly. The asymmetries were real. Not artifacts, not processing errors, real structural features within the coma that suggested something happening beneath the surface, something driving preferential outgassing from specific regions of the nucleus. Now, before we go further, I need to emphasize something important. When we talk about anomalies and unexpected behavior, it's crucial to remember that our sample size for interstellar objects is exactly 3. 3 visitors in 8 years. Our baseline for what's normal is essentially non-existent. What seems anomalous might simply be revealing the true diversity of objects formed around other stars in different chemical environments. That said, the patterns we're seeing with 3I/Atlas are pushing even that generous interpretation. One of the most puzzling developments came in early November. Multiple observatories, including ground-based facilities in Chile and space-based platforms, reported something extraordinary. The tail of 3I/Atlas, that characteristic streaming of dust and gas that makes comets visually spectacular, appeared to diminish significantly. Some images captured on November 7th showed a dramatically reduced tail structure compared to observations just days earlier. This tail loss sparked immediate debate within the astronomical community. Was this a temporary fluctuation in outgassing rates? Had 3I/Atlas experienced some kind of surface event, perhaps a collapse or sealing of active vents? Or was this indicative of something more fundamental about the object's composition and structure? The timing was particularly intriguing because it occurred right when Tianwen-1's observations were revealing those structural asymmetries. Avi Loeb, the Harvard astronomer who's become synonymous with interstellar object research through his controversial interpretations of Oumuamua, immediately suggested that the tail behavior warranted closer examination. While stopping short of invoking artificial origins, which he's done with Oumuamua, Loeb pointed out that the temporal correlation between the tail loss and the Tianwen-1 structural observations might indicate active processes within the nucleus that we don't fully understand.
Other astronomers took more conservative positions. They noted that cometary activity is inherently variable. Nuclei rotate, exposing different surface regions to sunlight. Subsurface ice pockets can suddenly breach the surface crust, creating temporary increases in outgassing that then subside. The tail reduction might simply reflect the chaotic, unpredictable nature of cometary evolution as an object approaches the sun. What made the situation more complex was the water vapor mystery I mentioned earlier. Remember, the swift observations showed water outgassing at distances where it shouldn't be possible through normal sublimation. The mechanism proposed by Bodewitz and Xing, with those distributed ice chunks acting as secondary sources, is elegant, but it raises another question. What ejected those ice chunks in the first place? The traditional answer would be carbon dioxide and carbon monoxide. These volatiles sublimate at much greater distances from the sun than water ice. As they transition from solid to gas, they expand violently, fragmenting the surface and launching material into the coma. We've observed this process countless times with solar system comets, but the scale of water vapor production from 3I/Atlas, that fire hose quantity, suggests an enormous amount of ejected ice, more than you'd typically expect from CO and CO2 outgassing alone.
This is where compositional analysis becomes critical. The JWST spectroscopy from August revealed those unusual chemical ratios I mentioned. What exactly was unusual? The details haven't been fully released in peer-reviewed publications yet, but preliminary reports suggest differences in isotopic ratios. The deuterium to hydrogen ratio in water molecules, for instance, can tell us about formation temperature. The carbon monoxide to carbon dioxide ratio reveals information about the protoplanetary disk environment where the comet formed. If 3I/Atlas formed in a protoplanetary disk with different temperature gradients, different stellar radiation environments, or different elemental abundances than our own solar nebula, its chemistry would reflect that. We'd be looking at a frozen sample of conditions around another star, potentially one with a very different spectral type than our Sun, an M dwarf with lower ultraviolet output, an F star with higher luminosity. The possibilities are vast, and each would leave distinct chemical signatures. The James Clerk Maxwell Telescope observations of hydrogen cyanide are particularly relevant here. HCN production rates that triple in just 1 week indicate dramatic acceleration of nuclear activity. But hydrogen cyanide doesn't just tell us about outgassing rates. The molecule itself is a biosignature precursor. In the right conditions, with water and energy, hydrogen cyanide can polymerize into adenine, one of the nucleotide bases in DNA and RNA. I'm not suggesting 3I/Atlas is delivering life to our solar system, but it is delivering complex organic chemistry from another stellar system. Then there's the carbon dioxide mystery that's emerged from the most recent analysis. Multiple observation teams, using both JWST and ground-based infrared spectrographers, have measured carbon dioxide levels in the coma that are extraordinarily high, at least 16 times higher than typical solar system comets. 16 times! That's not a minor variation, that's a fundamental compositional difference. Romain Magiet from the Royal Belgian Institute for Space Aeronomy has proposed an explanation that's both elegant and sobering. He suggests that the elevated carbon dioxide isn't necessarily a reflection of 3I/Atlas's formation environment. Instead, it might be the result of billions of years of cosmic ray bombardment during the object's journey through interstellar space. Here's how that works. Cosmic rays, high-energy particles accelerating through the galaxy, constantly bombard objects in interstellar space. These particles have enough energy to break molecular bonds in surface ices. When you have a mixture of water ice and carbon monoxide ice, which we believe is common in cometary materials, cosmic rays can break those molecules apart, creating reactive fragments called radicals. Over time, millions of years, those radicals recombine in new configurations. Carbon monoxide plus oxygen from water molecules can form carbon dioxide. The process is slow but relentless. Laboratory experiments simulating this process, where researchers bombard ice mixtures with high-energy particles, produce exactly what Magiet predicted: significant carbon dioxide production, along with a reddish, carbon-rich residue, both of which have been detected on 3I/Atlas. The implications are profound. If cosmic ray processing can so thoroughly alter the surface chemistry of interstellar objects, then the idea that these visitors are pristine fossils from other stellar systems, frozen time capsules preserving formation conditions, might be overly optimistic. We might be looking at objects whose surfaces have been fundamentally reprocessed during their interstellar journey. The chemistry we observe might tell us more about the galactic environment between stars than about the protoplanetary disk where the comet originally formed. It's like trying to read a letter that's been left outside for 100 years. The original text might still be there, but it's obscured by layers of weathering and degradation. But here's a glimmer of hope that emerges. 3I/Atlas reached perihelion, its closest approach to the Sun, on October 29, 2025. At that moment, it was just 126 million miles from our star, well inside Earth's orbit. The intense solar heating at perihelion could sublimate enough surface ice to expose deeper layers that have been protected from cosmic ray bombardment. Fresh material from the interior, still bearing the original chemical signatures from the comet's birth around another star. Cyrielle Oppetom from the University of Edinburgh emphasized this possibility when she noted that the next few months of observations, particularly using JWST and ground-based telescopes as 3I/Atlas emerges from solar conjunction in December, will be absolutely critical. If we can detect pristine material beneath the processed surface layer, we might still be able to deduce where this object came from, which star system, what kind of protoplanetary disk, what formation conditions. The timing is actually perfect in a way. 3I/Atlas disappeared from view in late October as it passed behind the Sun from Earth's perspective, but it's expected to re-emerge in early December 2025, moving outbound on its hyperbolic trajectory. On December 19th, it will make its closest approach to Earth, coming within about 168 million miles. Still distant, but close enough for detailed spectroscopy with our most powerful instruments.
As 3I/Atlas rounded the Sun at perihelion, its closest point on October 29, 2025, it was temporarily hidden from Earth, positioned on the far side of our star, in perfect alignment so only a handful of interplanetary spacecraft, Tianwen-1 included, could monitor the event. The observations from China's Mars orbiter and other international probes during this window were invaluable. They saw the coma swell and contract, the tail fluctuate, and for a brief period all but disappear, sparking an urgent global debate over the cause. Scientists watched, running real-time models, searching for signs that the intense solar heating might trigger fragmentation, vent sealing, or catastrophic loss of volatiles, but the comet remained stubbornly unpredictable. Throughout this perihelion passage, telescopes worldwide continued coordination. Hubble, JWST, ground-based observatories, waiting for 3I/Atlas to re-emerge from its conjunction. New images and spectroscopic data are anticipated as the comet moves outbound in December, with predictions that the fresh exposure of its interior will grant an unprecedented look at primordial chemistry, the untouched record of its birth environment. This will be our best chance to unravel its origins. Even so, many mysteries remain. The hydrogen cyanide release is accelerating, the carbon dioxide levels are confounding, and the comet's polarization shows a mix of icy and dark material not seen in any solar system cousin. Pre-discovery and current data suggest ongoing variable cometary activity, even when the comet was ridiculously far from the Sun, reinforcing the notion that volatile compounds unfamiliar to our solar chemistry may be at work. The global collaboration surrounding 3I/Atlas marks a turning point. Chinese, European, and American teams have freely shared imaging, spectra, and analysis, each seeking consensus in the face of the unknown. This unity underscores a simple truth. Every interstellar object is a messenger, carrying fragments of distant worlds, preserving questions and answers we're only beginning to ask. In its silence, as it slips away past Mars this winter, it leaves behind a trail of data and speculation, an unfinished story, and a reminder that those cold numbers are not just scientific results, but also testimony to our desire to understand our place in the universe. What makes this December observation window so crucial is not just proximity, but also the timing of post-perihelion evolution. When a comet rounds the Sun, the thermal shock is immense. Surface layers can crack, peel away, or slough off entirely, exposing subsurface materials that have been locked away for billions of years. If 3I/Atlas follows this pattern, the December observations with JWST and Hubble could reveal chemistry that was protected from cosmic ray processing during its interstellar journey. Pristine ice, original molecular ratios, the actual fingerprint of its birth star system. But there's another wrinkle in this story that emerged just as the comet passed perihelion. Multiple spacecraft monitoring 3I/Atlas from different vantage points, including Stereo A, Stereo B, SOHO, and the GOES-19 weather satellite, all recorded something unexpected. The comet brightened far more rapidly than models predicted. Not just a little brighter, significantly brighter than typical Oort cloud comets at similar distances from the Sun. Qicheng Chang from Lowell Observatory and Carl Bathams from the Naval Research Laboratory documented this anomaly in a paper posted to Archive. They wrote, and I'm quoting directly here, "The reason for 3I's rapid brightening, which far exceeds the brightening rate of most Oort cloud comets at similar radial distance, remains unclear." That's scientific language for "we don't know what's happening and it's bothering us." The proposed explanations are intriguing. One possibility is simply velocity. 3I/Atlas is moving fast, over 70 kilometers per second relative to the Sun at perihelion. That speed might create unique sublimation dynamics as the comet tears through the Sun's intense radiation environment. Rapid heating of volatiles that don't have time to equilibrate thermally could produce explosive outgassing, dramatic increases in coma brightness, and unusual dust production rates. But the alternative explanation is the one that keeps astronomers up at night. What if the rapid brightening tells us something fundamental about the comet's internal composition? What if 3I/Atlas contains volatiles or molecular structures that simply don't exist in solar system comets? Materials formed in a protoplanetary disk with different chemistry, different temperatures, different radiation environments. If that's the case, then every anomaly we observe, the excessive water vapor, the extreme carbon dioxide levels, the unexpected brightening, they're all pieces of the same puzzle, a chemical profile that reflects conditions around another star. This brings us back to the fundamental question that's been haunting interstellar object research since Oumuamua. How representative are these visitors of the broader population of objects drifting between stars? We've now observed exactly 3 confirmed interstellar objects in 8 years. 3 data points. From those 3, we're trying to extrapolate the characteristics of potentially trillions of objects wandering through the Milky Way.
Recent analysis by researchers studying Atlas survey data suggests that the density of interstellar objects in our local galactic neighborhood might be lower than initial estimates, perhaps 0.001 objects per cubic astronomical unit. That's sparse, far sparser than the optimistic projections made after Oumuamua's discovery. If that density is accurate, then each interstellar visitor is even more precious as a data source, because we might wait years or even decades between detections. The technological implications are significant. The Vera Rubin Observatory, which serendipitously captured 3I/Atlas during its commissioning phase, will begin full science operations soon. With its unprecedented survey speed and sensitivity, Rubin is expected to dramatically increase our detection rate of interstellar objects. Current projections suggest we might find 1 per year, possibly more. That means within a decade, our sample size could grow from 3 objects to perhaps 15 or 20, enough to start identifying patterns, enough to distinguish between typical interstellar chemistry and genuine anomalies. Now, I want to address something that I know many of you are thinking, because I see it in comments and emails constantly: the speculation about artificial origins. Let me be clear about where the science actually stands. There is currently zero evidence that 3I/Atlas is anything other than a natural object. Every observation, every spectrum, every image is consistent with a comet that formed around another star and was subsequently ejected into interstellar space through gravitational interactions. That doesn't mean we shouldn't look. In fact, we have an obligation to look, to examine these visitors with every tool available, because the only way to definitively rule out artificial origins is through thorough, rigorous analysis. But it does mean that we need to be intellectually honest about what the data actually shows. Anomalies are not evidence of alien technology. They're evidence that our models are incomplete, that nature is more diverse than our limited experience suggests. The Tianwen-1 observations have given us something that no ground-based telescope could provide: a simultaneous, independent verification of the comet's behavior during its most critical phase. While Earth-based observatories lost sight of 3I/Atlas as it passed behind the Sun, China's Mars orbiter maintained visual contact, documenting the entire perihelion passage from its unique vantage point 30 million kilometers away. That continuous monitoring revealed the subtle structural asymmetries, the localized brightening, the tail fluctuations that have become central to understanding this object's true nature. Now, as we move into December 2025, the scientific community is preparing for what might be the most important observational window yet. JWST's scheduled observations will use multiple instruments: near-spec for spectroscopy, near-cam for imaging, potentially MIRI for thermal measurements. The goal is comprehensive characterization of the post-perihelion coma, looking for evidence of fresh ice exposure, new volatiles, changes in dust production rates. Anything that might tell us whether the intense solar heating stripped away the cosmic ray-processed surface layer to reveal pristine material beneath. Hubble's contribution will be equally crucial. Ultraviolet spectroscopy can detect hydroxyl radicals, atomic oxygen, sulfur compounds, all signatures of specific chemical reactions occurring in the coma as sunlight breaks apart molecules. The sulfur to oxygen ratio in particular is diagnostic of formation conditions. High sulfur suggests formation in a cold outer disk region. Low sulfur indicates warmer inner disk formation. By measuring these ratios in 3I/Atlas and comparing them to solar system comets, we can begin to constrain where in its parent protoplanetary disk this object originated. ESA's JUICE spacecraft, currently en route to Jupiter, will also attempt observations in November, though at a much greater distance than the Mars orbiters. The data won't arrive until February 2026 due to transmission constraints, but it will provide yet another independent perspective, another set of measurements to cross-validate the findings from other instruments. This is what 21st century astronomy looks like. Not a single telescope making isolated observations, but an entire global infrastructure, ground-based, Earth orbit, Mars orbit, Jupiter transit, all coordinating to study a single object from every possible angle. The data volumes are staggering. The computational requirements for processing and analyzing all these observations are immense, but the scientific return is unprecedented. And here's what that return might actually tell us. If the December observations confirm that the extreme carbon dioxide levels are indeed due to cosmic ray processing, as Magiola suggests, then we have our first direct evidence of how interstellar space chemically transforms objects during their journey between stars. That's not a disappointment. That's a revelation. It means every interstellar visitor carries two stories: one about where it came from, encoded in its interior composition, and another about where it's been, written in the altered chemistry of its surface. If the post-perihelion spectroscopy reveals pristine material with chemical ratios that don't match solar system objects, then we have confirmation that protoplanetary disk chemistry varies significantly from star to star.
That has profound implications for planet formation theory, for understanding the diversity of planetary systems, potentially even for assessing the likelihood of habitable worlds around different stellar types.
But beyond the pure science, there's something deeper happening here that I think deserves recognition. The Tianwen-1 observations represent a symbolic milestone. For decades, space exploration was dominated by a handful of Western agencies: NASA, ESA, the Soviet space program, and its Russian successor. The participation of China's space program in cutting-edge astronomical research, not just as a contributor, but as a provider of unique, irreplaceable data, marks a fundamental shift in how humanity explores the cosmos. This isn't about geopolitics or national prestige. It's about the simple fact that the more eyes we have scanning the skies, the more instruments we have gathering data, the more perspectives we bring to scientific questions, the better our understanding becomes. 3i/Atlas is teaching us about interstellar chemistry, yes, but it's also teaching us about ourselves, about our capacity for cooperation when confronted with questions that transcend borders and ideologies. As 3i/Atlas continues its outbound journey, moving through Virgo and Leo in December, fading from magnitude 12 to 13 by year's end, it will gradually slip beyond the reach of all but our most powerful telescopes. By mid-2026, it will be too faint for detailed spectroscopy. By 2027, it will just be another faint point of light, indistinguishable from distant stars. And eventually it will disappear entirely, racing back into the darkness between stars at 70 kilometers per second, carrying with it whatever secrets we failed to extract during this brief encounter. But the data will remain. Thousands of images, spectra, measurements, all archived and available for future analysis as new techniques and new theoretical frameworks emerge. Every pixel captured by Tianwen-1, every wavelength recorded by JWST, every photon counted by Swift, they all constitute a permanent record of this moment when a piece of another star system passed through our own. And we were ready, we were watching, and we asked every question we could think to ask. In the end, perhaps that's the real message 3i/Atlas is delivering. Not a message in any intentional sense, not some alien communication or artificial structure, but a reminder that the universe is vast, that it contains wonders we're only beginning to catalog, and that every object traveling between stars carries information, history, chemistry from places we may never visit. And it's our responsibility, as the only species we know of that can build telescopes and spacecraft and coordinate global observation campaigns, to pay attention, to gather that information, to preserve it, and to keep asking what it means. So when you look up at the night sky this December, knowing that somewhere up there, too faint for your eyes, but visible to our most sophisticated instruments, an ancient piece of ice and rock is rushing past Earth on its way back to interstellar space. Remember that you're witnessing something that happens only a few times per decade. And remember that we're living in the first era of human history when we have the technology to truly study these visitors, to learn from them, to piece together the story of how our galaxy makes comets and planets, and perhaps life itself. That's the real discovery. Not any single measurement or spectrum, but the realization that we're finally becoming capable of reading the messages written in starlight and ice, in chemical ratios and orbital mechanics. 3i/Atlas won't be the last interstellar visitor. As Vera Rubin begins full operations, as our detection networks improve, we'll find more, and each one will teach us something new about the galaxy we inhabit and our place within it.